And thanks to everyone who helped me clean the blackboard. I did not to get to participate. All right. Okay, let me find out where we were yesterday. Oh, theorem. All right. Yeah. So. Yesterday, towards the end, what we figured out is that rank 3 fibrations, so we had rank 1 fibrations, and those are the same as Mori fiber spaces, Mori fibrations. And then we had rank 2 fibrations. These correspond to Sarkisov links. And then rank 3 fibrations, they correspond to elementary relations. And we never were particularly interested in continuing, but my assumption is that go to rank 4, you will have so relations. You can usually, we will see this today, you can sort of, you can represent them as walking along a disk, just like in geometric group theory or in group theory in general. And then I sort of am guessing that if you have a rank 4 vibration, this will give you sort of the, I don't know, spheres among Sarkisov links, and then 5, 6, 7, and then just continue with spheres of higher and higher dimension. And up to now, we were not really interested in those, but I'm like putting this out there if you have an idea what to do with it. Okay, and then so the theorem that goes along with it is that actually any relation between Sarkisov links is generated by these elementary relations, meaning that any relation between Sarkisov links is a product of conjugates of these relations and the trivial relations. So in particular, so in particular, it's a bit too close. So if we remember the notation from yesterday, so let's say X is some, I don't know, for simplicity, let's say this is a smooth. Let's say is this a Mori fiber space. Oh, okay. Fix this. Ça marche? OK. Okay. Let's say we have memory fiber space. Then Birmori, this was the group weight of birational maps. Birational to X. Okay, then this is generated by Sarkisov links. And the relations, the generating relations are elementary relations. So here, just to remind you, a groupoid is just like a group, only that you cannot always compose elements, but you can always invert them, and there's a neutral element, and it's unique. Okay, so I wanted to give a very, very vague idea of how to prove this, and it's very, very vague because I need to somehow vaguely explain something vague about the minimal model program. But the idea of how this is proven is very geometric. Okay, so I'm not going to go into any technical details anywhere, specifically not for the MMP. So I'm sorry, that what? So, right. Okay, so for me, these are if you have, let's say, F1, F2, this is an automorphism of Mori fiber spaces. You're unhappy. Do you prefer that I put 1? Oh, sorry. So, okay. F1, F2, Sarkisov links. And then if F1 and F2 inverse have the same base point, so let's say F1 and then F2, sorry, if F1 inverse and F2 have the same base point, you blow up, that means you blow up the same thing, and then maybe, let's say we have links of type 2. Okay. Do it first. F2 and then F1 and then F2. Let's say they are links of type 2. Okay, and let's say F1, the inverse of F1 blows up the same point as the one of F2. So that means that the composition is an automorphism. Okay. And so an automorphism over B. What? A times F1, E F2. I'm sorry? Yes, okay, yeah, you have, sorry. Let's say this is A. Okay, and then have what? Sorry, you can have an automorphism, F1, and then another automorphism. Yeah. There's possibly an inverse somewhere. So, no, because I'm, yeah, okay. Yeah, okay. Oof. Yes, yes, exactly. Okay. Any other relations that you would like to add? All right. I'm not, right, I'm, maybe I can add here plus the trivial relations. I'm not exactly sure what the people in group theory prefer, whether they prefer to add things like that or not. Why not? Okay. All right. Okay. So again, the proof is going to be very vague. So if you have a lot of questions, that's either because I'm not being precise enough, or because maybe you don't know the minimal model program, or because you are unhappy that I make. Okay, so let's see. So I have a relation of Sarkisov things. Yeah. There are two, I mean, yes. So wait. Okay. You can take the identity here and here, yes? No, but you... yes. I mean, no, it's... oh, I see. So, okay. Yes. Yeah. Absolutely. I think otherwise you would not have anything left. All right, so let's say we have a relation. Among Sarkisov links. And of course, I've forgotten to add something in the generator set. So here's Sarkisov links and automorphisms. Of more fibrations. And that's Serge marked. So by this, I mean, if I have two more fibrations, I want there to be an automorphism on top and on the bottom. Among Sarkisov links and automorphisms of more fibrations. Okay, so then okay, so I have my sequence of Sarkisov links and automorphisms, and then I just take the common blow-up of all these maps. So of these ones. All right. And so if T has picker rank 2 or 3, we just blow up some more points that maybe are not coming from anyone in the relation. Okay. And now what we want to do is we start the minimal model program or minimal model programs from T. Okay. And as the minimal model programs go, all the xi's are outputs of some minimal model program. So all these sequences of blow-ups, they are some type of minimal model program starting from T. But T can be very complicated, and there might be more outputs, more ways to blow down -1 curves or orbits of -1 curves. Okay, so these are among the outputs of the MMPs. There might be more. So when I say minimal model program, I mean contracting orbits of -1 curves that are 2 by 2 disjoint. So I need the pairwise disjoint because if I have a Galois orbit like this and I contract one curve, 1 minus 1 curve, so I always have to contract everyone in the orbit, so simultaneously. But if I contract one, then the other one becomes a 0 curve, so I cannot contract the other one as well. Okay, so this does not. This I cannot contract as an orbit. Okay, so now one can put all these minimal model programs in a geometric, one can look at them in a geometric way. And that's by representing these MMPs in a polyhedral cone. Okay, so this gives a polyhedral rational cone. Okay, and that encodes the MMPs. And we take a section, okay, and then here on the section we see a bit more. So I don't know. something like that. Okay, and let's say, so this is a polyhedral cone. This is a polyhedral cone of divisors. Okay, and the cone has some sort of chamber decomposition that corresponds to steps in the MMP. Actually, this carries a fan structure. So crossing, so somewhere in the middle, we have the ample devices. We have ample divisors. Okay. And then somewhere outside we have we have kx, and then oh, maybe that's a stupid way to do it here. Maybe we have kx, okay. And then we take one of these divisors, and we draw a line to kx. And every time we cross from one chamber to the next one, this is a step in the MMP. Okay, so this, and this is here, and then here we have some ample divisor. And on the way, we cross chambers. And they are exactly steps in an MMP. So this is sort of the way, so this is also called an MMP with scaling. Because the classical MMP is with respect, you contract curves that are negative with respect to the canonical divisor, but there is not really a priori a lot of reason to stay with the canonical divisor. There are lots of other divisors, it's just that we don't really know them. The canonical one is the only one that we actually know. So scaling with MMP gives you a way to do contractions with respect to other divisors if you like to. And this scaling gives you these other options. And an MMP is just very geometrically following a line. So this is, yes, okay. So this is sort of, I mean, we are on surfaces. So on surfaces, the minimal model program is just contracting -1 curves or orbits of -1 curves. But in high dimension, proving the MMP was very difficult, and this is the geometric way they proved it in higher dimension, in very vague terms. Okay, so they really started to do sort of convex geometry instead of the MMP. Okay. Yeah. Here. Yes, I can. I can, but I have to, if you want to be more precise, I have to. So, okay. Okay, this is in the set of divisors, you look at equivalence classes of divisors that have the same ample model. Ample model being that oh, sorry, this is in some sort of Rn. Sorry. Yes, yes, thank you. Yes. So it's n. I think it's. I don't know where the one. It's the divisor, so I don't know. It's up. Okay, thank you. I have this. Yes. I'm sorry. Now, what is this? Okay, so this is the set of pseudo-effective divisors, and on them you want to. This is a cone, and you get the cone. It is rational polyhedral. Okay, yeah, not always true. Not that one. Okay. I mean, so this is the, let's say, this is, I don't know. So this is a linear combination of the canonical plus some ample divisors. That is still pseudo-effective. And the AIs, they're all non-negative. They're all A naught, KT, and then the AIs, sorry, they are ample. So we choose the AIs. So I would like to be very rude. This is exactly the idea. This is exactly why I wrote vague idea. Because I did not want to go into these type of details. Because unless somebody is used to the MMP, the details are not really relevant for the idea. I mean, you want to have your discussion recorded, there's a ball here. Okay. Okay. Sorry, I repeat. This is happening in the divisor class groups, divisors up to numerical equivalence. Okay. We have some magical cone in here that is chosen in a particular way. And somewhere in the cone, in the interior of the cone, there is one sort of chamber that represents that contains ample divisors, or the ample divisors. And okay, and so the construction of the cone is made so that Kx is not in the interior of the cone. And then we can put a line from some ample divisor to kx and follow it, and that's an MMP. That's really, so yeah, as you guessed, there's a lot of technicalities in there, but I did not want to go into them. Where are the steps? Okay. Okay, now what is interesting is that, so the boundary of the cone, I mean the cone has a boundary, and part of it represents non-big divisors. Okay. This means that when you cross to the boundary that is represented by a non-big divisor, your dimension drops. Your MMP loses in dimension. Okay. So here, maybe, say here, this is and I don't know, this is, let's say, we need it, yeah, so let's say this section is like something like, I don't know, let's make it a curly M. And then the non-big boundary, like I put a plus here because maybe not everyone in the boundary of this cone is in the non-big boundary. So when we cross to the non-big boundary, this means the MMP makes a step. So it does a step. Let's say x to b, and the dimension of b is strictly smaller than the dimension of x. So the outputs of the MMP would be x, because afterwards we lose in dimension. We don't want to be that harsh with our variety. So in particular, the biggest, so on the boundaries, the biggest windows, they correspond to Mori fiber spaces. So this is a Mori fiber space. And again, I'm going to be very vague about the technicalities on which windows I should pick and so on. And in fact, so let's say on this boundary, we have, so okay, this was, let's change the dimension. Let's assume that the section is something three-dimensional and the boundary is two-dimensional. Okay, so we have and this is the boundary. So the biggest windows, they are Mori fiber spaces. And then what do I say, one window of codimension 0 in the boundary, they correspond to Mori fiber spaces. And then the windows of codimension 1 in this boundary, they correspond to Sarkisov links. So this is proven in a paper of Bacon and McKernan. So basically, imagine you have maybe two MMPs. Oh, this is not good. And let's say these are two windows. And then crossing from one window to the other would be applying a Sarkisov link from one Mori fiber space to another. So, and then what we show is that windows of codimension 3 in this boundary correspond to rank 2, to rank 3 fibrations. R plus 1. So here we would have rank 3 fibrations. Okay. Okay. And now, which order? So now, since we go back to our initial relation, f1 up to fn equal to 0, and we noticed already that the Mori fiber spaces x1, x2, blah blah blah, involved in these relations, they're among the outputs of our MMP, starting from T. So they're represented on this big boundary somewhere. So some windows on the boundary, they are representing our x1s, x2s, etc. And the same way, some windows of codimension 1 represent f1 up to fm. Might be more. Okay. And now, so basically we have something of codimension 3, and then we have the Mori fiber spaces. So this is on the boundary, and then going from one to the other here is a Sarkisov link. I mean, we saw that rank 3 fibrations correspond to relations among Sarkisov links. So they are sort of set up in disks on the boundary. Okay. And so now we take the dual. Take dual graph. Of the fan on this boundary. So in this case, this would be, we have 2, 3, 4, 5, 6 points. And then we relate points if they are neighboring surfaces. And the point here becomes a polygon. And then we put the a barycentric subdivision. So I get a point for the rank 3 vibration, and then I relay them with with lines. If sorry, for every Sarkisov link, I get a line to the Sarkisov link. Sorry, for every I get a line from the center to the center of these segments for every Sarkisov link. All right, so this is the graph I construct out of my boundary. And then the fun part is, so that actually this boundary is isomorphic to a sphere of dimension the pica rank of T minus 2, where a disk, say a disk of this dimension. And since we chose the pica rank of T to be big enough, these are of dimension rho of T minus 2, they are at least 2. So they are simply connected. And then the construction that we made to get this graph means actually that also the graph that we get from the boundary is also simply connected. And then so let's say, so this gives us a graph, let's say G, and G is also. Yes, yes, but yes. I wanted to, yeah, I know. Okay, and then, so, okay, let's see where we are. We have a relation F1, Fm. This makes up, they correspond to Sarkisov, to a codimension 1 windows on the boundary of this polyhedral, of this fan. Okay. And then so they're Sarkisov links, so they sort of pass around along the windows of codimension 1. And then when we do our construction, they start passing around, passing along the two skeleton of the graph. And it's a relation, so at some point, this is a closed loop that passes along the boundaries of disks. Our graph is simply connected, and so we can fill up, so we can contract the path, or equivalently, we can fill it up with disks whose centers have rank 3 vibration. Okay, let's see if I. Okay, so this is the vague idea. As Stefan and Serge commented, there is a lot more to it, what I said, but I really just wanted to give you the idea that there's a part that is technical, which is for MMP people, and then there is a part that is very geometric and like really like drawing up relations in a group. Did I go over time? How much time? Oh, thank you. 15 minutes. Okay. All right. I wanted to do some applications. And I wanted to prove one of them, but I think I will just list them. Like, yeah. Go for it. Exactly, yes.
But you way to
yes. But if you have... No, so you have one path is represents one decomposition of Sarkisov links, and then you have another path. So this gives you a loop. And you can fill the interior of this loop with disks that are represented by rank 3 fibrations. So it is not necessarily that you have that all your relations are disks represented by rank 3 fibrations, but it's more like that you can fill them up with disks representing rank 3 fibrations. And this is what you get. This means exactly that your relation is a product of conjugates of elementary relations. Okay. Because you will find it easy to find relations that are not elementary relations. Is it okay as a, yeah? All right, so, okay. So first, let's say we have an algebraically closed field, and then there is a lemma that says if so the group BRP2 has no finite quotients. Okay, the proof is an application of the Nutter-Castelnau theorem. We have generators, the standard involution and automorphisms, and you just have to show that if you have a homomorphism from this group to a finite group, all the generators are in the kernel. And we have the generators, and then you can go. Okay, and then the other theorem that I wanted to give is that is by Gonnier, I think in 2013. It's an annex in the paper where Stefan and Serge show that the Cremona group is not simple. So he shows that BP2 is not isomorphic to an amalgamated product of two groups, and the product is amalgamated along their intersection. We can get isomorphism to amalgamated product of two groups along their intersections modulo one relation. This is a result by Jeremy, but we cannot get this close. Okay, so now So there's no Sarkisov program in here a priori, but now we can show that these are wrong over non-closed fields by using the Sarkisov program. So, where do we have? So, I try to put things in chronological order. So, there exists a homomorphism from here P2 R to a direct sum of two sets where I is uncountable. And this is surjective. And the kernel is the group of the derived subgroup. And then we can do a lot better than a direct group. So there is, so if K is still perfect, so if K has a Galois extension of degree 8, then there exists a homomorphism from the Cremona group over K to a free product of Z2s along over some, and the index set, so the number of factors is at least as big as K. So we can do much better than the Cremona group. Okay, and then in the spirit of this one, we can get amalgamated products. So this is the amalgamated product of group G1 and the group G2 along their intersections. And G1 and G2 are subgroups of pair P2, preserving a pencil of conics, of lines, preserving, so G preserves a pencil of lines through a point, and G2 preserves a pencil of conic through two conjugate points. There is, yeah, you're right. Thank you. Okay, and then there's a reason why we only get to Z2. Okay, that's because so the Noether-Castelnuovo theorem tells you that P2 over C is generated by the standard involution and automorphisms. Now, so the automorphism group is PGL3 over K. And since if K is algebraically closed, this is P SL3 over K. And this one is generated by involutions. So a corollary of the Noether-Castelnuovo theorem is that the Cremona group over an algebraically closed field is generated by involutions. And we don't know, I recall you, we don't really know generating sets of pair P2 over fields that are not C or R. I mean, we do, but the list is huge. and so on. So much. So Stefan and Julia showed that BRP2 over a perfect field is always generated by involutions. Okay. And then there are some more results in higher dimension. So, for instance, Jeremy, Julia, and Yegor showed that starting from dimension 4, the Cremona group over C has a projective homomorphism towards a free group generated by as many elements as, like the complex numbers, as many elements as the complex numbers contain. So basically any group generated by uncountably many elements is a quotient of the Cremona group. So you get a lot of interesting results in higher dimension. I had planned to explain you a bit how we proved this result using the Sarkisov program and relations, but I don't have time. So yeah, this is all I wanted to say. Wait, I wanted to do some advertising. In 2016, Jeremy and his PhD students organized a Cremona conference in Basel for 2 weeks. First week workshop, second week conference, and it was awesome because it was warm, and so in the afternoon after the talks you can just jump into the Rhine and let yourself float down for a bit and then repeat. It was absolutely great. We had fondue by the Rhine. Why everyone wants to have fondue in summer, I still don't know, but okay. And we're going to have anniversary conference next year. So this is the Cremona conference 2026. And it will be from 31st August to 4th September in Basel. This will be the workshop week, and then the week afterwards, which is 7 to 11 September in Neuchâtel. Now, in general, at the end of August, the river, the Rhine, is still warm. You can still swim in it. And then later in September, it becomes a bit cold, but the lakes, they grow colder more slowly. So we can still jump in a lake. Okay. So yeah, just keep it in mind, put it in your calendar, don't forget.